this design of 90-degree hybrid coupler using short-circuited coupled parallel 3-line. So let's get started. Before going to the design, let's know what is a coupler. A coupler is a 3 or 4 port passive microwave component which is used for power division and power combining. This is a 90-degree hybrid coupler which has 4 ports. This is the through port, this is the output port. This is the S parameter matrix. The J's indicate the 90-degree phase difference between through port and coupled port. The 1/2 factor indicates the equal power division. Here we are using the quarter wave transformers which make this device have very narrow bandwidth. Let's see how we can increase the bandwidth of this device. This is the coupled line whose characteristics can be modeled in this way using capacitors. In this case, the phase difference between input port and output port is 90 degrees. So if we are using a parallel coupled 3-line, it would be 180 degrees. Parallel coupled 3-line has more coupling factor when compared to parallel coupled 2-line. Parallel coupled 3-line increases the bandwidth of the device by giving more coupling. So this we are going to use in our design and increase the bandwidth. This is the design. It shows 2 sections of the coupler. This is the parallel coupled 3-line. These are the design equations which we are going to follow in our design. Find the impedances. Before going to the design, we need to have substrate details. These are the details which you can see here that I'm going to use in this design. So key points which we have to remember before going into the design is the coupling factor equal to 1 gives the widest bandwidth, but not practically possible. So we can decrease it to 0.8 or less. So K equal to 1 gives equal power division, but it can be changed to have the widest bandwidth. The line-to-line distance between the coupled line should be at least 200 micrometer, or otherwise the effects of conductor thickness height would be seen. So maintain it at least 200 micrometer. The MATLAB code which I've written to find the impedances. Any other tool can also be used as Python to write the code and find impedances. So once we have the impedances, we can jump into the design. So these are the labeled bits and the lengths of the components. Here I'm using microstrip lines for design. These are tabulated here. These widths and lengths can be calculated using line calculator tool in ADS, or any other calculators can also be used for calculating the widths and lengths of the microstrip lines. This is the schematic. You can see that this is the 3-line coupler. These are the vias. These are the T junctions which need to be added to properly generate the layout. This is the microstrip line added to increase the distance between the lines so that the layout is properly generated. The layout view, after generating the layout view, add ports, define substrate, and go for simulation. These are the results which I've obtained. A fractional bandwidth of 20.3 is obtained here, which indicates it's a wide band. Phase and amplitude balance is also good. Phase balance of 0 is obtained at the frequency of interest. Similarly, a phase imbalance is also good in the band of interest. There's an observation here. As the line-to-line distance between the coupled lines decrease, the fractional bandwidth increases. So I conclude saying that we have achieved a fractional bandwidth of 20.3 and phase imbalance of 1 dB, 3 degree, and amplitude imbalance of 1 dB in the band of interest, which is 500 megahertz. Thanks for watching this video.